Okay, so our book derived this formula for us. The force on a plate is an integral from A to B. That depends on your width and your depth functions. This is your width, this is your depth, and this is the weight density of water. So we've got this plate that's a semicircle. So we like to put things in the X and Y grid so that we can start doing some math with them. And it's a plate that has a radius of 5. So this, if I draw a circle that's centered at 0, 0, it's got 5 all the way across. So the equation of a circle that's centered at the origin is x squared plus y squared equals the radius squared. So that's the equation for that circle going around. We'll probably need that to help us define either the width or the depth. And let's draw this plate in there. Intuitively, water and gravity is pushing things down, so that should be down. It looks like this. Actually, it's like this. That's our plate. This is the water, right? And they tell us for this problem that it's submerged, 2 meters of it is above the water, and then 3 meters is below. Okay, so if we were to do some integration with this, we're going to get negative for an area, which might be tough to do. So it's the same answer as if we were to find out this. This is 2. I just flipped it so that now we're in a positive region. Okay, so we want to come up with a function for the width and for the depth of this region. And since they tell us, the limits are with respect to the y-axis here, going up and down. I mean, you could flip this again, rotate it, make it the x-axis, but we can just integrate with respect to y. And the weight density of water is 9,800. Let's see the width. So everything we do has to be in terms of y. We'll want to remember that. And then we're integrating with respect to y, so this y-axis is key. Remember, we chose that because y equals 2 and y equals 5 are those limits of integration. We could find out these points too, but I think it's going to be a square root, like the square root of 21 or something. Okay, so the width is dictated by the value for x, and so x depends on that equation of the circle. Right, so the width is, if you solve for x in this equation, you'll get x equals the square root of 25 minus y squared. So the square root of 25 minus y squared is our width. Okay, so the depth, depending on what y value we have, it should be 3 at its maximum. The depth should be 0 at the minimum. So if we do y minus 2, then when we plug in our minimum, we have 0 for depth, just like it's supposed to. And then it gets bigger and bigger and bigger until we get to y equals 5 when it has that depth of 3, right? Because this thing has a radius of 5. 2 meters are above water, so 3 meters are withstanding that pressure. Okay, now I think we got everything. This one can be solved using u substitution. We'll let u equal 25 minus y squared, the entire inside of that square root. Then du equals negative 2y. So we don't have dy. We could get it. The algebra is going to be kind of weird. Because if you divide this by 2, then you can multiply this whole thing by 2. I'll make this negative, that way we can multiply this by a negative. So that's a negative 4,900 I'm pulling out. This is eventually going to be square root of u. If I distribute that negative 2y, and then at negative 2, I get negative 2y plus 4. Does it say we can use a calculator? No, because the algebra is going to get trickier there. You'll have dy, you'll have du, but here, let me pull up an online calculator for the rest of this because we don't quite have du here. So I went to symbolab.com. I've got this. I've got our integral typed in. I used x instead of y just because I don't know if it can do it with respect to y. It probably could if you typed in y if I gave it a try. But it looks like the total force is 240,319 and 0.40703.